Hello, physics students. This is as advertised, a discussion mostly about orbital motion, planetary or satellite orbital motion, specifically in circles, but it also gives us a really good opportunity to talk about what it means for an object to be massive. What is fundamental about massive objects? If you need to skip ahead for purposes of time to the circular discussion and the orbital gravitational stuff, please feel free. But if not, just hang on for a sec. So, can you hear the bell in the back? Okay, so what does it mean to be massive? What does it mean for an object to be massive? That's kind of an obscure question, but to physicists it really means two different things. All right, in no particular order. One, and maybe don't write yet until I've dialed this in just the way I like it. One, it means to be to create and to feel the effect of gravitational field. So that's a number one. All right, everything, I mean, by definition, objects that are massive do that. They create gravitational fields and they are affected by them. I wish this looked better like that. Sure, fine. I wish it was centered, but hey, come on. That's one thing. All right, so we're all pretty familiar with the idea that, sure, I mean, Earth makes gravitational field, and you drop a ball and it falls towards Earth. So gravity is something entirely connected with the concept of mass. All right, number two is that even in locations in the universe where there's very, very little gravitational field strength, and an object that is a mass isn't necessarily pulled by any gravitational field or experiences no gravitational force, objects that are massive by definition, what does it mean to be massive? It means objects that are massive resist acceleration. Acceleration. Yeah. Those are the two things that it means to be massive. I can't help it. That's a little better. Sure, fine. All right, so everything that's massive, and it's hard to say thing. I mean, what are these things that aren't massive? Okay, well, they're photons or energy, and they're not massive. Yeah, okay, they're neutrinos, which are, they're so tiny. All right, fine. So when we say thing, of course it sounds like we're saying mass. But, so, things that are massive, by definition, definitely do each of these two things. What they do is, every object that's a mass creates a gravitational field. Every object that's a mass is affected by the gravitational field that it's in, via a gravitational force. And every object that is, well, objects that are massive, that have any mass at all, to some degree resist acceleration. All right, and these are tied up in two ways of talking about mass. The one over here we call, well, oddly, not coincidentally, yeah, we call this gravitational mass. And over here we call this inertial mass. Right? The idea of inertia, right? Inertia by definition is resistance to change in velocity, which is the same thing as saying resistance to acceleration. Acceleration. Newton's first law, right? Objects at rest tend to stay at rest. Objects in motion tend to stay in motion. That's an incomplete statement of Newton's first law of motion. The complete statement being, it's called the law of inertia, the complete statement being that objects at rest will stay at rest, objects in motion will stay in motion at a constant velocity until they're acted on by an unbalanced force. But what that doesn't capture is, to what degree things will resist acceleration. That has to do with how much mass they have. And when you see, you will likely see questions in your physics career about, hey, which one of these objects has the most inertia? Well, which thing is most resistant to acceleration? The things that are most resistant to acceleration are the things with the most mass. All right, so mass as some people say, is a measure of inertia. Inertia is not a number. It's not a quantity. It's an idea. It's a principle. It's a property of matter, inertia. I have to check the books for that one. But it's not a number. Mass is a number, all right? Depending on how you talk about it, it's either, you know, the degree to which objects create or are affected by a gravitational field, or it's the degree to which objects resist acceleration. All right, so massive objects do both of these things. We're very likely to gloss over that fact, and it's okay to some degree to gloss over it, but there's a profound difference. What's nice about the following few slides is that we'll go pretty deeply into this part, the gravitational mass part, but then we'll make a link that is required to link gravitational mass effects to inertial mass effects. So if you haven't started bleeding from the ears yet, hang on, we'll talk about orbital circular motion stuff. But first, we got to talk about basic gravitational stuff. All right, so here's a universe populated by a single object. What does this object do? Well, it doesn't really do anything except it creates. It creates in the space around it, creates a gravitational field that we call G in all space around it. My first year folks have heard this already, and this is a review, and that's okay. So, that field, G, importantly, is a vector. By definition, the vector always points at this location in space, that red dot. That's not a thing. It's not another object. It's a place in space. There's a vector G that, you know, maybe looks like that here. There's a vector G a little farther away that maybe looks like this. There's a vector way out here that looks like that. It gets smaller. All right, so G, two things about gravitational field. One, G points radially inward. Two, G gets weaker as distance from what I'll call the field maker increases. Okay, more definitively, here is an object of mass big M, and I will define that this thing has a spatial radius capital R, and well, here's a place that we're going to locate here in space, and we're going to say that place is a distance R, and guess what? This R doesn't mean radius. R means distance. R more technically is a vector that locates this point relative to another point, but for now, for us, it's okay to say that R is the distance. Very importantly, R from center of M to point in space. What point? What point in space? Any point you want. All right, I've picked an arbitrary one right here. Now, by definition, gravitational field, how strong is a gravitational field? Well, it depends on a few things. Two things. One is it depends on how massive the object is that makes the field. The more massive an object is, the stronger the gravitational field it creates. Now, if you want, we could sort of call this like gravitational. We said, right, there are masses kind of can be thought of in two ways, as gravitational mass or as inertial mass, right? So this stuff right now has nothing at all to do with the fact that masses are hard to accelerate. It has everything to do with the fact that by their nature, masses, Einstein says, deflect the fabric of space-time and thus create gravitational field. All right, nothing about inertia here. Everything about the gravity causing, that's a crappy way to say it, but the the gravitational nature of mass. Let's just say that. So the stronger, the more massive an object is, the stronger the field it creates, and that's a direct relationship. All right. The farther away, as we said, a location is from the center of an object that creates a field, the stronger the field is. And that goes like this, except it happens to go as r squared. Purposes of that aren't too important. It has to do with spatially the fact that if you draw this field, the field lines that we could sort of say look like this, spread out in a couple of different dimensions. They spread out like in the plane of this paper, but also they spread out in the plane that I can't draw, the one coming like toward me. Here's a line coming toward me that that's a crappy drawing. So the squared part, again, not something to worry about, but there is a physical significance to it. Okay, that's fine, except for the fact that g isn't measured in kilograms per meter squared. All right, so what we do is we put the universal gravitational constant out in front of that. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. That's something that will be provided for you in any class you take where you have to solve problems numerically. All right, and it actually tells us that g, that means that g is measured in these units, Newton meters squared per kilogram squared. That's the big G part, times m. So here's the times m, that's times one factor of kilograms, divided by r squared, that's a factor of meters squared. So g is measured in those meters squared and those meters squared go. These kilograms with one of those kilograms. We get that g is measured in newtons per kilogram. Gravitational field strength is measured in newtons per kilogram, which is to say that gravitational field strength is a measure of gravitational force per unit mass. Now, this m means m placed in m's field. And we could say, parentheses, hypothetically, if there were a mass placed here, what amount of force on m in m's field? If I were to put an object here, right here, see? If I were to put an object right here, how much gravitational force would that object feel? Well, it depends. Depends on how strong the field is at that location. All right, the field is a ratio of force applied per unit mass. Okay, so two ways to express it. This is the fundamental way, which says if all we know is how massive an object is in space and how far away from that object we are, that's how strong the field is. If we know something about another object placed in that field and how much force that object experiences, then we say, oh, the field must have been strong enough to do that. Now, a very popular sort of question is to say, at the surface of this planet, g surface, well, the gravitational field at the surface goes as g mass of the planet divided by, now I say capital R, where capital R is not the same as little r. Capital R is this. Capital R is the planet's spatial radius, because capital R is the distance from the center of the planet to the planet's surface. That's the planet's radius. So if you do this for Earth, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times 5.98 times 10 to the 24th kilograms, happens to be Earth's mass, divided by 6.38 times 10 to the 6th meters. Don't forget to square that. If you do that for Earth, guess what you get? You get that g surface Earth is 9.8 newtons per kilogram. And it doesn't only work for Earth. You take any object at all, if you know if it happens to be a sphere, and you know its mass, and you can plug into that formula and figure out what strength that object's gravitational field is at the object's surface. So what does this mean? It means that when we stand on the planet Earth, on Earth's surface, generally for every kilogram of mass that we place in Earth's field, there's a gravitational force of 9.8 newtons that are exerted on it. And that's why we say that Fg, when we say how much does an object weigh on Earth? Well, if an object has a mass of 1 kilogram and gravitational field strength on Earth's surface is 9.8 newtons per kilogram, then the gravitational force exerted on that object by the Earth is 9.8 newtons. Or really, usually we refer to this as an object's weight. How much does an object weigh? Well, that depends. It depends on how massive it is. And it depends on where it is in the universe and the gravitational field strength at that location in the universe. Okay? So, two ways to express and or calculate G. Or maybe to relate G to other important stuff. And again, this is all about gravitational stuff, right? This mass down here is also a gravitational mass. Nothing at all to do so far with, hey, that thing was hard to get moving, that thing was hard to stop, that thing was hard to accelerate. Nothing to do with that so far. Everything to do so far with the fact that by their nature masses create and are affected by gravitational fields. Okay, now, a universe populated by only two objects. What do they do to each other? Well, at this location, and everywhere along that circular arc that's all the same distance r from the center, that's a r, center of object 1, there's a gravitational field made by mass 1. And that is big G times m1 divided by how far we are from m1 squared. Everywhere on that, everywhere equidistant from mass 1, the gravitational field is that strength. All right, we actually put a mass there, and now this mass feels a gravitational force that's equal to m, quote, mg. But if we want to be a little more specific and careful about how we express that force, we would say, well, the gravitational field, or sorry, the gravitational force on 2 by 1, so I'm saying Fg on 2 by 1, the force exerted on mass 2 by mass 1, well, it depends on 2's mass and 1's field strength. All right, and so that's going to look like this. That's going to be that Fg 1 is m2 times this stuff. Or we're going to write it as, I'm going to just change the order in which I multiply things because I can do that if I want. Thank you very much. G m1 m2 over r squared. And that's called Newton's law of universal gravitation. If you want to know G 1, I'm just writing it again for some reason, m1 m2 over r squared. If you want to know the force, the gravitational force that two objects exert on each other, what you have to know is how massive is each one, how far apart are they. Or what you have to know is how massive is one and how strong is the field that the other one makes. Okay? But this is another expression for gravitational force. F means force, not field. This, one of the tough things is G means field. It doesn't mean force. F means force. Now, a couple ways to talk about, right, there's the magnitude of the force on 2 by 1. What about the magnitude of the force on 1 by 2? Well, there's an exhaustive way to do it, and I'll do it fast, right? Everywhere at this distance away from object 2, there's a gravitational field that points toward 2, made by 2. There's G2. That's GM2 over this same r squared, because 1 and 2 are both a distance r apart. So then if we want the gravitational force exerted on 1 by 2, we do m1 times g2. And what that gets you is m1 times this stuff, which, guess what, is g m1 m2 over r squared, which is the same as this. That force looks like this. FG12, and ooh, my drawing is an ugly time, but look at these two forces. Boy, are they ever exactly the same size and in opposite directions. Oy, sure. That's Newton's third law, right? I'll say here that FG21, FG12. This says they are equal and opposite. When I make them vectors, it means they're vectors of the same size, but they point in opposite directions of each other. These are Newton's third law force pair. Man, is this good review for midterm time. Okay there? Okay. Now, many of us have looked at free fall questions where we drop things like, say, in this room. Yeah? And you can do those in a couple of ways. One is using what are called kinematics equations. Another one is to use conservation of mechanical energy. Those will yield the same results. When we take things and go to a larger astronomical scale where mass m is located some big distance away from big M's center, this is a different free fall case. I'll say not near Earth's surface. Here's the type of thing we can talk about. All right, well, how strong is big M's gravitational field where little m is? All right, so okay, so everywhere at this, that circle around big M, there's a gravitational field that points inward, that points inward, that points inward, that points inward. It's all the same size, and that gravitational field G made by 1, by definition G m1 over r squared, where this distance r is from here to here. Okay, great. Ooh, look, acceleration. Suddenly we're talking about acceleration. Now, if we talk about acceleration, it means we're talking about the effect that a force has on an object. And that suddenly gets us to Newton's second law. And Newton's second law says that A is net F over m. Most of us see that as, use that primarily like this, F equals ma, net F equals ma. But really acceleration depends on net force applied to an object and how much the object's, or how massive the object is. And boom, suddenly we've talked about the fact that by their nature masses resist acceleration. By their nature masses have inertia. This has nothing to do with the fact that masses create gravitational field. This has nothing to do with the fact that masses, by their nature, experience gravitational force. Newton's second law is about things resist, things being objects, things being masses resist acceleration. That's a fundamental difference between talking about, this is really gravitational, and there's no need to use these subscripts. I'll show you why in a minute. But it is neat that they're different things, and they're different phenomena. So I want to show you something that, let's see, so net F. So the net F is Well, let's see. The force exerted on this object, Fg, is, well, m times g, and my subscript crap now is getting wacky, but this is g made by big M, and this is mass m little m, fine, okay. This is mass little m also. All right, so that gravitational, this net F is Fg over little m. And that acceleration, well, is g big M little m over r squared, because that's the gravitational force divided by this little m. This little m. And what that does is it takes this out of there. And what we get is the acceleration is g big M over r squared. The acceleration that an object has the same, is the same thing as the gravitational field strength. All right? So to say, what's the numerical value of this? Well, on the surface of the Earth, gravitational field strength is 9.8 newtons per kilogram. And if you drop an object in that field, it accelerates at 9.8 meters per second squared. What I'm not saying here when I write those 9.8s, I'm not saying that's the answer to every problem. It's not the answer to any problem except one at Earth's surface. With this object out here in space, G's not going to be 9.8, so A's not going to be 9.8. All right, and so my guys have talked about that G field strength and acceleration are the same thing. Well, they kind of are and they kind of aren't. What it really tells us is that this gravitational mass and this inertial mass are the same thing. Even though they're different phenomena that masses demonstrate, they're the same. Which again is maybe more detail than a lot of people need, but it's pretty freaking cool. And so as long as we define the Newton in the way that we do, we define the Newton to be a kilogram meter per second squared, then it allows us to say that inertial mass and gravitational mass are the same thing. And people have done like exhaustive experimentation to be sure that inertial mass and gravitational mass are equivalent. We take it way for granted, but people have gone to pretty great lengths to do so, to prove that they're the same thing. Like they've proven it to 1 part out of 10 to the 13th or something like that, which is absurd. It's cool. I mean, it's a pretty fundamental thing that we take for granted scientifically all the time. So if it's not true, we're kind of screwed. So it's good that people spend a lot of time proving that for us. Okay? Okay. Now, so because we end up with this A is G M over R squared, which is really the same thing as G, what we get, it's nice to be able to look at, I'll say, or G as a function of R. This inverse square relationship looks like that. All inverses are curvy like that. This one happens to be curvy such that, you know, if like this gets, you know, this has that coordinate. If we cut this in half, then this gets 4 times bigger. 1, 2, 1, 2, 3, 4. All right, so my curve isn't very good. But an inverse square graph, an inverse square relationship means that whatever you do to one thing, you do the opposite squared to the other. Okay? Now, the weight, M's weight is the same thing as us saying, what's the gravitational force? And that's G big M little m over R squared. All right, so there's a, if we want to do this as a free fall problem, the problem is we can't do we can't do the kind of conservation of energy problems that we've done before. You certainly can't do kinematics equations, because kinematics equations and the kind of standard conservation of mechanical energy problems that we usually do assume that little g is constantly 9.8, that acceleration is constantly 9.8, and that just is not the case for objects that are astronomically far apart like this. So those problems get a little bit different, and that's a topic for a different presentation. But what we do want to make sure we get to is this. This looks a lot like this one, except now instead of having this object sitting there some distance away, now this thing is moving. And in particular, we're going to say that it's moving in a direction like this, v, that happens to be tangent to that circle. And what we'll get is we'll get, well, just like we did before, no matter what, we get a gravitational force that looks like that. That gravitational force is perpendicular to this object's velocity. So what it can't do is make the object change speed, but what it can do and has to do is make the object accelerate. So therefore, it doesn't change speed, but it accelerates. That means it changes direction. And that force remains constant if the distance r here remains constant. So acceleration remains constant. Here's r. Acceleration remains constant, but the object can't change speed, so it changes direction at a constant rate, which means it moves in a circle. So objects that are moving in orbit are in free fall. The only force they experience is the gravitational force. They fall towards the object they're orbiting, but inertia keeps them moving along the path they're moving in. And what we're able to do is write a pretty standard net F equals ma statement to find orbital speed, among other things, but orbital speed's the kind of the interesting one perhaps for now. All right, so a simple net force, a simple free body diagram identifies Fg as the only force acting on little m. All right, so this is Fg equals ma. Well, this is an AC in the centripetal direction toward the center of that circular path. So this is v squared over r. Now, this r does mean radius of circular path. This r means distance from center to center. Because when we say Fg, we're going to say big G, big M, little m over r squared is mv squared over r. This r by definition doesn't mean radius of a circular path. It means distance between one object center and another. All right, but assuming that m is way, way bigger than little m, then these r's are the same thing. This r and this r are the same thing. There are cases in which it's not the same thing, where you have two objects that maybe look like this, and they're you know, close to the same mass, and what they do is orbit around a common center of mass. So there's a center of mass, say here, a little closer to the more massive object. This one moves around it like that, and this one moves around it like that, and that's called a binary system. And they both sort of wiggle or wobble around that center mass. Anyway, but for this case, which we're assuming right now, like a Earth satellite system, satellite is way less massive than Earth. So these r's are basically the same r. We can get rid of one of them here. The mass of the orbiter is irrelevant, and we can express the speed of the object in orbit like that. Important, this is the orbited object. Fair enough? So this gets us a discussion of centripetal circular motion stuff. It gets us a discussion of gravitational stuff. What also lives in here that maybe you didn't see is if we didn't get rid of that r yet, we get v squared over r is gm over r squared, and this is AC. This is gravitational field. That A again is equivalent to, that acceleration is equivalent to field strength. That's kind of neat. All right, so there's a lot that lives in there, but this is a standard kind of question. All right, so orbital speed depends only on how far you are from the thing you're orbiting. All right, and what's a inverse square root graph look like? Oh boy. Well, it's an inverse, so it's got to look like that. Yeah, no matter what, if r gets smaller, v gets bigger. So you got, if this was the sun, and you got Mercury going Venus, Earth, Mars, Jupiter. The farther planets are away, the slower they move. The longer their solar years are. All right. That's a long one, people. That's pretty deep, though. There's a lot to get to. A lot to get to in there. Yeah, I tried to talk fast, so I don't know how much double speeding you could do there. So I will. I hope this leaves you well. Oh, here's a standard kind of problem. All right. When you solve this, you'll get V moon is about 1,020 meters per second relative to the Earth, and you'll get that orbital period is about 27.4 days. You should confirm that you can do that. Okay? Okay. Bye.